Last week, we explored RNNs, LSTMs, and how they use word embeddings for language tasks, as well as the basis of attention. Today, we dive deep into the groundbreaking paper Attention is All You Need, which introduced transformers, revolutionizing language models. At the end of last week, we talked about LSTM with attention, and the attention part was only brought upon the communication between the encoder and decoder states, while the rest was still just using memory vectors. The transformer architecture, however, uses attention mechanisms for all communication between encoder and decoder states. And there you go. Attention is all you need, the name of the paper itself. On the left side is the encoder, and on the right side is the decoder. Let's start by explaining what's going on in the encoder and then the decoder. Before we go into the details, let's look at the animation from the Google AI blog post to just get an intuitive feel as to what the transformer does. In a nutshell, the encoder takes in all the source tokens, let them look at each other, update their representations, and repeat this however many times. As for the decoder, it's trying to generate a target token at every time step by looking at all the previous target tokens, then looking at all the source tokens, updating its current time step representation, and repeating this however many times until it reaches an output. This image summarizes what the transformer architecture is doing intuitively. The encoder consists of four major parts. 1. Input embeddings. 2. Positional encoding. 3. Self-attention. 4. Feed-forward. Starting with input embeddings, we've already learned this part. Every token in the input sequence gets converted into a vector and goes as inputs to the network. Next, positional encoding. Let's look at these two sentences. I eat cake. Okay, cool. Cake eat I. Wait, what? Keeping track of word order is super important, or else the meaning of the text could change drastically, and positional encoding aims to add context of word order in the input phrase on top of the word embeddings, where each positional encoding is unique. How it's done in the original paper is a bit unintuitive, and everyone moved on from this method anyways, so I'm not going to explain it in detail. But basically, it's these two functions that generated the positional encoding vectors for each word inputted, where POS is position, I is the vector dimension index, and D is the dimension of the word embedding. Nowadays, we usually just train additional vectors inside the model to add on top of the word embedding at the corresponding index. Moving on to self-attention. As we've already seen the basic idea of attention, self-attention is just the input sequence doing attention with itself. So every word in the input sequence looks at every word in the input sequence. However, attention is implemented a bit differently than the intuitive ideas we've discussed last video. This attention is called the query key value attention. Every word embedding will create 3 separate vectors by going through 3 separate linear layers respectively. Really just a matrix multiplication here, since there is no bias or activation function, etc., each with their own purpose. The query vector asks for information from the key vectors. The key vector says it has information to the query vector. The value vector is what finally gives the information. And this is the formula for attention between the trio. Basically, attention scores are computed between the query and the key, which then are normalized by dividing the hidden size, then multiplied with the respective value and summed together. And do I even need to explain this feed-forward layer? It's just a linear layer. Now, we'll pause for a second and acknowledge something about all these parts in the encoder. 1. Word embeddings are given independently. 2. Positional encodings are added independently. 3. Query key value are calculated independently. 4. Self-attention can be calculated at the same time. 5. Residual connections can be calculated independently. 6. Final outputs are calculated independently. Basically, all of them can be computed in parallel, leveraging GPU power. And this is a huge speed up over sequential RNNs/LSTMs. On to the decoder. The decoder consists of 5 major parts. 1. Input embeddings. 2. Positional encoding. 3. Masked self-attention. 4. Encoder-decoder attention. 5. Feed-forward. The input embeddings, positional encoding, and feed-forward are the exact same idea, so I won't go over them again. So what is this masked part of the decoder's self-attention? Well, in the encoder, every word is supposed to see every other word and do attention with every one of them. But the decoder in practice should generate the words one after another, and each word should only be able to see its previous words and itself. So in training, while we know what's supposed to be the output sequence, we still only allow the decoders each word to see its previous words and itself in the output phrase to compute attention, even though we technically know the whole answer. This whole part is just asking how important is the previous parts of the predicted sequence to the last predicted word for predicting the current word. As for encoder-decoder attention, that's using the decoder's self-attention output as the query and the encoder's output as the key and value to calculate attention. We've seen something similar to this last video, and it's really just asking how important is the parts of the input sequence to the last predicted word, also for predicting the current word. And if we think beyond just text, you've probably seen how AI can now see images or listen to speech.
How's your day going?
Hey, my day's going well. Thanks for asking. How about yours?
Glad to hear your day's going well. Mine's pretty good too. Thanks for asking.
That's because the query, key, and value don't have to be just words. They can be any kind of data that we can turn into numbers. For example, if you're generating an image from a sentence, we can use attention to compute how important each word in the sentence is to different parts of the image in generation. Or if you're converting speech to text, we could use attention to compute how important a piece of audio is to a word in a sentence. Since these types of data, text, images, audio, and so on, all have different numerical formats, we use the query key value matrices to transform them into a common dimension. This lets neural network models apply attention across different types of data, which we call cross-attention. Now, what about the multi-head part of attention? Well, there are a couple ways to do it, and here are the two common approaches. One is splitting the vectors. We break each word's query, key, and value into smaller chunks called heads. Each head computes attention separately, and then we combine them at the end, concatenating them head to tail. Another is by multiple sets of vectors. Instead of having just one query, key, and value per word, we have multiple sets. Each set calculates attention independently, and we simply add up the results at the end. Both methods allow the model to focus on different aspects of the data at the same time with different attention sets. I did skip over what residual connections and layer normalization is during this entire part, so let's quickly go over them. Residual connections are basically adding a block's input to its output. They make gradients flow through a network more easily. While layer normalization is just normalizing vectors independently, this is for the network stability. And that's about it for the transformer architecture. Let's sit back for a moment to look at this image and appreciate what the transformer is doing. Now, the whole transformer setup isn't just one encoder with one decoder block. The paper stacked 6 encoder and 6 decoder blocks, meaning the output of one block feeds into the next, repeating 6 times before reaching the final output. So, how does this connect to GPT? Well, if we just take the encoder and stack itself, we get BERT. If we take just the decoder and stack itself, we get GPT. Without an encoder, there's no encoder-decoder attention anymore. But remember cross-attention? The later AI models, like GPT-4, might have reintroduced something similar to process image and audio, but OpenAI hasn't shared the details on GPT-4 and so on. Now, before we move on, there's 2 things I need to talk about. One is the context window. This is the maximum number of words/tokens a model can process at once. Why does this limit exist? Well, it's mostly because of memory capacity and computational demands of self-attention. When you first feed a sentence into the GPT model, for example, I entered the cinema to watch a movie, all the word embeddings have to propagate through the network and calculate masked self-attention scores with each other. Let's say the model predicted the next output token to be but. Then it re-inputs this prediction to next time step's input to predict the next word. We don't have to re-input the already processed tokens. As with masked self-attention, the newly inputted token will not be seen by the previous tokens, and hence not update their attention representations. The only new computations involve calculating how this new token attends to each of the previous tokens by reusing the computed embeddings and attention outputs from the previous tokens. Now, for example, if you had a very long list of tokens, say 50,000 tokens, the new token's attention computation would need to attend to all 50,000 previous tokens, which can become computationally expensive. Storing and managing the representations and attention scores for all 50,000 tokens also requires significant memory. This is another practical reason for having a fixed context window size. That's also one of the reasons you sometimes see these language models suddenly forget some of the earlier content you've been discussing with it. Since, say, your conversation is now 50,000 tokens, but its context window is only 30,000 tokens, the language model's newest inputs simply won't do attention with the earlier tokens, and just discard them from memory to keep the conversation going. 2 is on tokenization. Before I described tokens roughly as words in a sentence, but the reality is a bit more technical. Tokenization uses a compression algorithm called byte pair encoding, BPE. This method, introduced in 1994 by Philip Gage, breaks text into smaller, reusable chunks, creating a dictionary to represent them efficiently. You can go look up the details yourself, or just check OpenAI's website to see how different GPT models tokenize text. Special characters, like non-English symbols or emojis, are usually stored in their Unicode byte representations. Now let's move on to the iterative improvements over the GPT family, starting from GPT-1. GPT-1 was simple. It just predicted the next word based on context over and over again. Its own outputs become future inputs, continuing until it generated a special token that told it to stop. OpenAI built GPT-1 by stacking 12 decoder blocks. But it wasn't exactly smart in understanding of language. It needed fine-tuning, extra training for specific tasks like translation, Q&A, and summarization before it could be used. Here's a diagram summarizing the additional architecture they used for different tasks for GPT-1. With GPT-2, OpenAI asked, can we train a model to understand language without fine-tuning? They called this idea zero-shot learning, meaning that the model could perform various tasks without extra training. I personally think the naming convention here is a bit ridiculous, but hey. So, what changed? Only 2 major things for the model architecture. 1. They reversed the order of concatenation and layer normalization in the model. 2. They massively scaled it up compared to GPT-1, with the following numbers on screen, going from 117 million parameters in GPT-1 to 1.5 billion parameters in GPT-2. And for training GPT-2, OpenAI believed that training on a larger, more diverse dataset will make the model better at general language tasks. So they scraped the entire Reddit, specifically posts with links to other websites that had at least 3 upvotes. This gave them a total of 45 million links, which they proceeded to extract all of the text data from all of them. After filtering, they ended up with 40 gigabytes of text data, which they called web text. Here's a cool part about training GPT models. They don't need an explicit feature label pairing data. Because what does GPT do? They just predict the next word in a sequence, and obviously the correct answer is already in the text itself. So the model simply learns by repeating this process of predicting the next word, calculating the loss compared to the real next word, input the real next word, predict the next word, calculate the loss compared to the real next word, and so on. They found the results a success. GPT-2, with its larger model size and larger diverse dataset, had language capabilities that emerged out of the blue. Now, moving on to GPT-3. It didn't change much architecturally. It was basically a massive scaled-up version of GPT-2. However, they introduced alternating dense/sparse attention. Dense attention is where a word looks at all the previous words, whereas sparse attention is where a word looks at some of the previous words, making computations more efficient. And here's a diagram as to how GPT-3 scaled compared to GPT-2. We went from 1.5 billion parameters to 175 billion parameters. Now, OpenAI also trained GPT-3 on way more data. Like, Common Crawl is literally a filtered web scrape of the entire internet. GPT-3 also introduced a new training method called few-shot learning, a better way to teach the model of tasks without fine-tuning. Basically, the model is provided with a task description and a few examples of the task being done. By seeing examples during inference, GPT-3 could recognize patterns and generalize to new tasks without additional training. Other names like zero-shot learning refers to having no examples and just a task description, while one-shot learning is just one example given. Now, GPT 3.5 is where people started hearing the name of ChatGPT, and I must correct a common misconception. GPT is not the same as ChatGPT. Like, sure, we say the GPT models are now capable of understanding language generally, but it doesn't, 1. Self identify as ChatGPT or as a helpful assistant. 2. It gets lots of facts wrong. 3. It isn't always positively toned. 4. It doesn't have censored topics in itself. Basically, what I'm saying is that GPT, while now it understands language, isn't ChatGPT. ChatGPT is a fine-tuned version of GPT, optimized for conversations between a user and itself. OpenAI has an image explaining how they trained it, but honestly, I have no idea about the exact details myself. And that concludes our current journey in natural language processing. AI has came a long way, from the idea of the perceptron in the 1950s to ChatGPT being released to the public in late 2022. Look at the AI industry now. A once planted seed has grown into a tree, now striving into forest with all these different directions of AI research and startups trying to push the limits of AI further. Like, look at this AI that can generate videos. Or maybe it's this other AI that's driving a car. Oh yeah, and the robot with AIs in them, walking around in labs. What's next? No one knows for sure. Papers are being released day after day, AI models get released one after another. The frontier of AI research is still wide open, just like any other discipline of study. And I really hoped this series of videos was able to give some insight into what AI is today, and maybe even inspire you to keep walking forest down this road somewhere, and pave way for the people that come after you, venturing down the road that you built. I mean, isn't this series of videos just for that purpose? I still got a lot to learn myself, and through this process of making these videos, I realized I'm not a big fan of making them. Until then, see you. Bye-bye.
이제는 나가야 할 때 자신을 태워 사라져가는 촛불과 닮아 있구나 수고를 새도 없이 떠밀려 던져진 날 속에 내 길을 갈 수 있기를 먼 날 언젠가는 돌이켜볼 기억 속에 미소 질 수 있도록 멀리 멀리 날아가고 싶어 밤하늘의 새처럼 별에 닿을 수 있게 이밤 또다시 찾아오겠지만 괜찮아 다 사라지네 괜찮아 괜찮아